Hello everyone, welcome to tutorial 3, question number 3. Now this question is the application of what we have studied so far. The question says that a condenser of capacity C is discharged through the inductance L and a resistance R in series, and the charge Q at any time t, it satisfies the equation given here. Now it has been given that L equals to 0.025 Henry, R equals to 50 ohms, and C equals to 2 into 10 raised to the power minus 6 farad. And when t equals to 0, charge q is 0.02 coulombs and the current dq by dt, that is rate of change of charge, is 0. Now these are basically the initial conditions or boundary conditions which will be used to identify the or find the value of the constants. Let's start with the question. Let's try to solve this equation which has been given over here. So we have L d square q by dt square plus R dq by dt plus q by c is equals to 0. Now to make it simpler for calculation, I'll divide the entire equation by L so that I get d square q by dt square plus R by L dq by dt plus q by c. Now I need to find out the value of q over here, the equation of q. So uh, let's substitute the value of R, L, and C over here. So the value of R is 250. The value of L is 0.025. Q is the variable, so we are not going to substitute the value of Q as of now. C is the capacitance, so 2 into 10 raised to the power minus 6 equals to 0. Okay, it should be LC, so this has to be multiplied with 0.025 into 2 into 10 raised to the power minus 6 is equals to 0. So this becomes d square q by dt square. Now on solving this, we get 10,000 in the numerator, dq by dt, and on solving this, so simply if I solve this one, I'll get 1 by 0.025 into 2 into 10 raised to minus 6. Now there are three decimal points, there are three numbers before the decimal. So I'll have 25 into 2 into 10 raised to minus 3 into 10 raised to minus 6. 25 into 2 will become 50, and I'll have 10 raised to minus 9 over here, which becomes 0.02 into 10 raised to power minus 9, or sorry, plus 9, or in simpler terms, it becomes 20 into 10 raised to power 6. So I'll just write down the value over here, 20 into 10 raised to 6, q is equals to 0. And this is just for the calculation, so I'll erase it up. Now, I got this equation, I'll convert this equation in the form of auxiliary equation that we have studied. So my auxiliary equation becomes m square plus 10,000 m plus 20 into 10 raised to 6 is equals to 0. Now I need to find out the roots of this equation. To finding out the roots, I'll use the simple equation, quadratic equation. So this will become minus b plus or minus under root b square minus 4ac over 2a, which further becomes minus 10,000 plus or minus under root b square, that is 10,000 or 10 raised to 4 square minus 4 into a is 1 and c is 20 into 10 raised to 6. Divide by 2 times 1, that is 2. So let's solve this up. You'll get 10,000 over here plus or minus. From here you can take out 10 raised to 6 common. So if you take 10 raised to 6, the root of 10 raised to 6 is 10 raised to 3. What will be left? Inside here in this part, 10 raised to 2 will be left. So that is 100. And here 80 will be left. So you'll be left with root 20 divided by 2. Or this becomes 10,000 plus or minus 10 raised to 3 into root 20 divided by 2. Now this on solving will give you two answers. The first one being minus 2764 The second one being minus 7236. Right, you can try it at your own and substitute the values in the final equation, which will give you the general solution over here. The general solution for this will become C1 e raised to the power m1x plus C2 e raised to the power m2x. Substituting the values of m1 and m2, you'll have a general solution as minus 2764. Now this x in this case is the time, because the change of charge is with respect to time. So this will be your QC being equal to C1 e raised to the power minus 2764t plus C2 e raised to the power minus 7236t. Now we need to find out the value of C1 and C2 using the initial boundary condition. Let's do it. So the equation of QC that we got was C1 e raised to the power minus 2764t plus C2 e raised to the power minus 7236t. Now over here, the initial condition is given in two parts. The first part says that at t equals to 0, the value of q is equals to 0.02. Let's substitute this value. So 0.02 will become, now if I substitute t equals to 0, this entire terms becomes 0, this entire terms becomes 0. Oh, sorry, not 0, 1. Why? Because anything raised to power 0 is 1. So 0.02 C1 plus C2 is equals to 0.02. This is your equation number 1. The second thing, the second condition, at t equals to 0, dq by dt is equals to 0. Now you are supposed to find out dq by dt. So the equation of q, I'll be differentiating it once with respect to t, so that I get minus 2764 C1 e raised to the power minus 2764 t minus 7236 C2 e raised to the power minus 7236 t. Right, so this is the equation I got. Now if I substitute the value of t equals to 0, dq by dt is by default 0, and if I substitute t equals to 0, this will become 1 and this will become 1. Why? Because anything raised to the power 0 is 1. The equation will become 2764 C1 minus 7236 C2 is equals to 0. Now equation 1 and 2, you can solve it easily. You can solve it either using elimination method or by substitution. I would prefer to solve it by substitution. It is quite easier. On solving equation 1 and 2, get the value of C1 to be equal to 0.032, and that too of C2 you get minus 0.012. These values we can substitute in the equation of Q, so that you get the final answer of Q, which is C1. In place of C1 you have 0.032 e raised to the power minus 2764t minus 0.012 e raised to the power minus 7236g. So this is the final answer for the equation of Q in terms of time t. Now let's look into the next question and see how that can be solved. This is another question which shows you the application of these differential equations. So there is an EMF E sine PT is applied at t equals to 0 to a circuit which contains capacitance C and inductance L in series. Now this current is satisfying the given equation. So this is the equation we are supposed to solve, and at the end we are supposed to prove that the current at time t is Et by 2L sine PT, where I is dq by dt, that is current is rate of change of charge, rate of flow of charge. So let's start with this equation. L di by dt plus 1 by C integration I dt is equals to E sine PT. Let's substitute the value of I equals to dq by dt over here. So you'll get L d square q by dt square plus 1 by C integration of I dt. So in place of I, you will substitute dq by dt. Dt will get cancelled and integration of dq will be q. So you'll get q over here is equals to E sine PT. Right. Now, the similar way we have done in the last question, I'll divide the entire equation. Now, in this case, I'll divide it on both the sides with L. So I'll get LC 1 by L C Q is equals to E by L sine PT. Now this is a whole non-homogeneous equation with some term being on this side of the equation also. So I'll be solving it in two parts. The first part, I'll solve it on the left hand side. Now over here, one important thing has been given, that P square equals to 1 by LC, and I can see 1 by LC over here. So this thing I can write down, d square by dt, d square q by dt square plus P square q is equals to E by L sine PT. So I use this part of the equation, the question. So the first part that I'm supposed to solve is this one, d square q by dt square plus P square q is equals to 0 to find out the general solution. The auxiliary equation over here becomes m square plus P square is equals to 0. This will give you m square equals to minus P square, or the value of m will be plus or minus Pi. Imaginary number because there is a negative root over here. Now for an imaginary number, the solution is given in the terms of trigonometric functions. So over here it will be cos of pt, or let's say I'll start from sine. So c1 sine pt plus c2 cos of pt. So I got these terms. Now I need to find out the particular integral or particular solution for this term. So for that I will be using the method of undetermined coefficient, because on the right hand side also I have E sine pt. So I'll use this equation QC rather than this one, since this is a cycloidal or periodical equation. The sinusoidal function is a periodical equation. So what we'll do is, we'll, instead of using this equation, I'll multiply this term, this equation, with t in order to avoid any of the uh, problem at the end. So what I'll be doing is multiplying this with t and sine pt, and multiplying this also with t with cos pt. The reason why I'm multiplying these two parts with t is because this is a periodical function, and if I differentiate sine twice, I'll get again sine but in negative. So that will get cancelled out and I won't get the final answer. So I need to substitute or multiply this equation by t. Now with this equation, let's multiply, differentiate this equation twice to be substituted, so which can be substituted in this part, right? So the first one is already there. If I differentiate it once, that is dq by dt, if I find out, I'll get c1 is a constant. First of all, I'll keep t as constant, so I'll get t cos pt, and then plus sine pt. Now c2 I'll keep constant, I'll keep t as constant, so I'll get minus t sine pt plus cos pt. Now double derivative will give me c1. Now this again will become okay. This whole equation will also be multiplied by p, because p is a term before time t. Now again I'll have p square c1 common over here, and then inner term will become, this again will be differentiated with the help of chain rule. So you'll get cos pt minus t sine pt plus cos pt. Right, and similarly the next part also, the first term, it will be a part of chain rule. So this will become minus sine pt minus t cos pt minus sine pt. This is what I'll get over here. Correcting some of the things over here, this p won't be on this side, rather than the p in this case, this p will be multiplied over here but not here, and in this case the p will be multiplied over here but not here. So you won't be having p square in this case, but yes, inside you'll have p cos pt and p square sin pt, and this will be p cos pt. Similarly, this will be p sin pt minus p square cos pt and p sin pt. Now you got this part, and if you simplify this one, you'll get an equation which is equal to c1 2p cos pt minus tp square sin pt plus c2 minus 2p sin pt minus tp square cos pt. Now, with this complicated equation, what we are supposed to do is we are supposed to substitute the value of q double dash in this equation. So let's do it and see what we get in answer. Okay, now I'll substitute the values of q double dash in the given differential equation. So the given differential equation, as we have obtained earlier, was d square q by dt square plus p square q is equals to e by l sine pt. Now this, I need to substitute the value of this second derivative of q, which turned out to be a big equation given by c1 2p cos pt minus tp square sin pt plus c2 minus 2p sin pt minus tp square cos pt. I'll modify this equation a little bit so as to make our calculation easier by separating the terms. So first of all, I'll take these two terms, this 2p cos pt and 2p sin pt. So in these two terms, I have 2p common, so I'll be left with c1 cos pt minus c2 sin pt. Similarly, I'll take tp square. Out of this, I'll take p square common. So I'll be having minus p square common, and I'll be left with c1t sin pt plus c2t cos pt. So this is I have obtained, and now q double dash further will be equal to, this is c1 cos pt and this is sin pt, c2 sin pt. Now this equation is what we have assumed to be our q. So this will become minus p square q, right? So q double dash is this equation. Now let's substitute this equation in this equation, the differential equation, so that I get the final answer. So this will become, in place of q double dash, I'll have 2p c1 cos pt minus c2 sin pt minus p square q. This is the value of q double dash. Then p square q is equals to el sin pt. Now over here, these two terms will get cancelled. Right. So I'll be left with 2p c1 cos pt minus 2p c2 sin pt is equals to el sin pt. Now on comparing the term, the first term, that is this part, there is no cos on the right hand side, so this will become 2p c1 equals to 0 or c1 equals to 0. Comparing the sign, I'll get 2p c2 or minus 2p c2 is equals to e by l. From here I'll get the value of c2 to be equals to minus e by 2pl. Right, so I got the value of c2 and c1. Let's substitute it so that I get the answer of qp. So the qp turns out to be what I have assumed, c1 sin t, c1 t sin t plus c2 t cos t. So sin t is 0 because c1 is 0. Only c2 component will be there. So I'll get minus e 2p l t cos t. Now, so the final equation of Q will be QC plus QP, which is equal to C1 cos PT plus C2 sin PT minus E T cos T by 2PL. Now we move towards finding out some of the things related to this initial conditions. Let's look out how this thing will affect our. The final equation of Q that we have got over here is Q is equals to C1 cos PT, or you can write down sin PT even, C1 sin PT plus C2 cos PT minus ET cos PT over 2PL. Now let's take these initial conditions. So first thing that has been given is at Q equals to 0. So at Q equal to 0, sorry, at T equals to 0, not Q, at T equals to 0, Q is equals to 0. So I'll substitute this equals to 0. So cos 0 is 1, sin 0 is 0, so this will become 0. So I'll get 0 equals to C2 cos PT. Cos 0 is 1, so this will C2, and this is minus ET by 2PL. Cos 0 is again 1. So I get the value of C2 to be equal to ET by 2PL. Okay. The time is 0. So this entire thing will become 0. Right. So this will become 0. Now again, next thing is given about the current. The current is also 0. So current is basically, we have seen dq by dt, the rate of change of charge. So I need to differentiate this equation, which will be PC1 cos PT plus PC2 sin PT. This will be minus because the differentiation of cos PT is minus sin PT. Now this I'll be doing it by uh, chain rule. So first of all, I'll keep the t as it is. So I'll get plus Et sin PT by 2PL, and over here P will be multiplied. And in the next case, I'll keep cos constant, so I'll get minus E cos PT by 2PL. So this is the dq by dt, and this is equals to 0. The current is equals to 0 at time t equals to 0. So at t equals to 0, this entire term is also 0. So I'll get this cos 0 is 1, so this will become 1. So I have PC1. This will become 0. Sin 0 is 0. This term will also become 0. And the last term, cos 0 is 1. So I'll get PC1 minus E by 2PL is equals to 0. Or this turns out to be C1 is equals to E by 2P square L. So I got the value of C1 and C2 now. I'll substitute to find out the value of Q. So Q is at C1, I have E 2P square L sin PT. C2 is 0, so this second term will become 0. And next is ET cos PT divided by 2PL. So this is the equation of the charge, but I need to find out, I need to show that the current at time t. So current is rate of change of charge again. So I need to find out dq by dt. So this again I need to differentiate. So this will become E t cos pt 2p square L. This is done. Now I'll be differentiating the second term, but this will be done by using the chain rule. So I'll keep t constant first. So I'll get plus E t sin pt by 2pl into p. And in the second case, I'll differentiate t and keep cos constant. So I'll have e cos pt by 2pl. Now, if you look it carefully over here, this p will get with this p square, and these two terms will get cancelled altogether. So I'll be left with only this term, and the term is also this p will get numerator will get cancelled with this denominator. So the current finally that I'll be getting over here is equals to e t sine pt by 2l, and that is what I need to prove. So hence true. Let's see the last question of this tutorial. A body executes a damped force vibration given by this equation. So you have to solve this equation. Let's see what is the equation over here. It's y double dash plus 8y dash plus 64y equals to 128 cos 8t. So this is non-homogeneous equation. So first of all, I'll find out the auxiliary equation, which will become m square plus 8m plus 64 equals to 0. Or the value of m will be equal to minus 8 plus or minus under root b square, that is 64 minus 4 into 64 by 2. This on solving becomes minus 8 plus or minus 64 minus 256, that is 192 or minus 192 by 2. So this will be minus 8 plus or minus 8 root 3 I by 2, or minus 4 plus or minus 4 root 3 I. So the solution over here consists of both real and imaginary parts. So this can be given as the component yc being equal to e raised to the power minus 4t for this minus 4. And since this is a complex term, so I'll get in bracket c1 cos 4 root 3t plus c2 sine root 3, sine 4 root 3. Now let's find out the particular integral. For that, what I have is these two terms. Right. So I'll assume this yp, the solution of yp, to be a cos 8t plus b sine 8t. The value of y dash will be minus 8a sine 8t plus 8b cos 8t, and that of y double dash will be equal to minus 64a cos 8t plus minus 64b sine 8t. Now if I substitute these values in the given equation, I get minus 64a cos 8t minus 64b cos 8t sine 8t. Now substituting these values, so this will be multiplied by 8. I'll get minus 8 or minus 64a sine 8t plus 64b cos 8t and 64y. So 64a cos 8t plus 64p cos 8t. This whole thing is equal to 128 cos 8t. So this term of cos will get cancelled by this term of cos. This will get cancelled by this one. So I'll get this only equation, and left 64a sine 8t plus 64b cos 8t is equals to 128 cos 8t. Comparing the sine terms and cos terms separately, so we'll have the value of a being equal to 0 and the value of b being equal to 2. right? Because there is no sign term on the right hand side. So we can compare cos and cos directly, and I'll get the value of b equal to 2. So if I substitute the value of b equal to 2, the assumed solution over here, it becomes something different. It becomes a is 0, so b, only b will be there. So 2 sine 8t. So my final answer will be the summation of yp and yc. So y will be equal to e raised to the power minus 4t c1 cos 4 root 3t plus c2 sine 4 root 3t plus 2 sine 8t. So this will be my final answer. Well, that's it for this tutorial. Thank you so much.